Hello, and today we're going to do 1.5 for college algebra, which is all about complex numbers. So recall that complex numbers involve some sort of imaginary component. In general, complex numbers take the form of a plus bi. So we want to be able to understand that this is standard form of a complex number. We can add, subtract, multiply complex numbers and find complex solutions to quadratics. Now, if I had a quadratic like this, x squared minus 2x minus 3, we'd probably want to solve by factoring. Well, what multiplies to negative 3 adds to negative 2? That'd be negative 3 and positive 1. And then we can use the zero product property, setting each of those parenthetical expressions equal to 0. Therefore, we would get solutions of 3 and negative 1. It's also important to note, if I were to graph this quadratic, it would look something like this, where we get x-intercepts at 3, 0 and negative 1, 0, because those are real solutions. Real solutions also are x-intercepts. Now, if I were to graph x squared plus 4 equals 0, it would look something like this. Well, we all agree that y equals x squared would be this graph right here. Let's be x squared. So x squared plus 4 would look like this. Everything has just been shifted up 4 units. Well, you notice that x squared plus 4 has no x-intercepts. Therefore, it has no real solutions. There we go. Therefore, no real solutions, which means it is also not factorable. However, let's say I were to try to solve it. Let's say I didn't know any of that stuff. X squared plus 4 equals 0. Well, because I have no b term, I would just simply probably solve by square rooting. So I would subtract 4, x squared equals negative 4, square root. I square rooted, so we get plus and minus. And then I can do the square root of 4 and the square root of negative 1. Well, I know that the square root of 4 is 2. And as we recall, the square root of negative 1 is I. So we would get plus and minus 2i here. So that's kind of the bulk of where we're going today. So, complex number. What is a complex number? A complex number has both the real and imaginary unit. If it just has the imaginary component, it's pure imaginary. If it just has the real component, it's just pure real. It says no i's, and this has no reals. The nice thing is, with the same structure, they have to be equivalent if and only if the coefficients are equivalent. So, as I reminded you from a previous section, but nice to know, the square root of negative 1 is I, which means I squared has to be negative 1, which should make sense, because if I have I equals the square root of negative 1, I can undo this square root by squaring both sides, therefore I squared equals negative 1. I to the third, I'm going to skip for a second, because I want to talk about I to the fourth. Well, if we remember, if I had something like x to the power of a, and I multiplied it by x to the power of b, we all remember, if I'm multiplying by the same base, I add exponents, a plus b. So I can use this to sort of explain what I'm going to do here. For example, I to the fourth is the exact same thing as I times I, where the exponents add up to 4. So I can do squared squared, right? Because again, 2 plus 2 equals 4. Therefore, I could recognize that I squared, I already know, is negative 1. And here I already understand that this I squared is also negative 1. So I get negative 1 times negative 1, meaning that I to the fourth has to equal positive 1. And if I were to follow this up even further, I to the sixth would be I squared times I squared times I squared, which would be negative 1 times negative 1 times negative 1, getting me negative 1. And then I to the eighth would be I squared times I squared times I squared times I squared. Well, that's going to give me 4 negative 1s. Going to be positive 1. Therefore, every even exponent, this pattern alternates. So I to the 10th would also be negative 1, and I to the 12th would be positive 1, etc. forever. I to the third, well, that's simply going to be I squared times I. So I get negative 1 times the square root of negative 1, or negative root negative 1. Less interesting, I think, than I to the fourth. Now, adding and subtracting complex numbers, we treat them as like terms. So 4 plus negative 3 is positive 1, and 8i minus 9i gives me negative 1i. Here, I have a subtraction sign, so I can distribute that negative or keep, change, flip, however you remember it. So I get 3 minus 4 is negative 1, and I get negative 6i plus 2i, or negative 4i. Multiplying. Well, I can still do it just like any sort of binomial, aka the distribution property, also known as foiling sometimes. 4 times negative 3 is negative 12. 4 times negative 9 is negative 36i. 8i times negative 3 is negative 24i. 8i times negative 9 is negative 72i squared. We all agree that I have like terms I can combine right there. Now, recall that so distribution works the same. The only extra thing that happens is we have to recall that I squared is negative 1. So I'm going to replace this I squared. I get negative 72 times negative 1, which would be positive 72, which means I can combine those like terms as well. So negative 12 plus 72 gives me positive 60 for my real component. Negative 36i minus 24i gives me negative 60i. Following that same logic, 3 times 4 is 12. 3 minus 2 times negative 2i, negative 6i. Negative 6i times 4, negative 24i. Negative 6i times negative 2i, positive, negative times negative is a positive, 12i squared. Replace the I squared with negative 1. So 12 times I squared, 12 times negative 1, negative 12. Combine my real components. 12 minus 12 is 0. Combine my imaginary components. Negative 6i minus minus 24i gives me negative 30i. So this first one would be complex. You don't need to write this down, but it's nice to remember. And this would be pure imaginary. Going back to those vocabulary terms from this slide right here. Okay. Next, Dividing complex numbers. Just like if you remember, having the square root in a denominator is considered bad form. Same idea. You do not want i's down there. It's considered bad practice. So we do actually use a little trick. Now, if I flip back a slide, when I multiplied things out, you'll notice that my first and my last terms turned out to be the real aspects. Negative 12 is a real number. Negative 72i squared turned into positive 72, which was also a real number. So when I multiplied, the only time I had imaginaries were in the middle. So I want to get rid of my middle terms. So this idea actually comes from difference of squares. If you recall, x minus 2 times x plus 2. If I were to multiply this out, you'll notice that the middle two terms are simplified out. They undo each other because I get opposite operations happening right here. So in order to do that, we multiply what's called the conjugate. The conjugate is simply that same idea, where I'm going to flip the symbol of the denominator. And more importantly, I have to do it to both sides because this whole thing as a concept equals 1, and you can always multiply by 1. So I'm going to multiply. I'm still going to keep the 4 and 3i, but again, this is a plus sign, so I have to do a subtraction sign. From there, I'm just going to distribute on the top and the bottom. So 4 times 2 gives me 8. 2 times negative 3i gives me negative 6i. Negative 3i times 4 is negative 12i. Negative 3i times negative 3i would be positive 9i squared. 4 times 4 is 16. 4 times negative 3i is negative 12i. 3i times 4 is positive 12i. 3i times negative 3i is negative 9i squared. And again, as we talked about, my two middles in the denominator are going to cancel out, which is awesome because now I just get 16 and this negative 9 times negative 1, so positive 9, so I end up with 25 as my denominator. Up top, we get 9 times negative 1 for negative 9. We get 8 minus 9, so negative 1. And then we get negative 6i minus 12i, so negative 18i. And here, there's nothing I can simplify out. What I could simplify out is when all three of these things are divisible by the same thing. For example, we've had something similar, like when we're using the quadratic formula. When you get something like 3 plus or minus 3 square root 5 all over 3, I could divide all those things by 3. But here I can't, so I'm all good. And here's just a walkthrough example of that first problem I did on the first slide, explaining how we went about doing that business. And as I said, imaginary solutions do not appear as x-intercepts. Solve. Okay, no, there's two ways you can go about solving this. The first thing, of course, you would look at it and try to factor. But unfortunately, this is not factorable. And it's not factorable because, spoiler alert, there's no real numbers that work for this. They're both imaginary solutions. So there's two ways you can go about solving this. We will do both. First would be the quadratic formula. And second would be completing the square. So let's start with the quadratic formula. Quadratic formula being x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. We can identify our terms in the standardized form of ax squared plus bx plus c equals 0. So in this case, my a is 1 because I have a 1 out in front of my x squared. My b term would then be 6 because I have 6 attached to the x, and my c term would be 10 because that's my constant. So let's plug all those in. We get negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 10 all over 2 times 1. Negative 6 stays. 6 squared would be 36. 4 times 1 times 10 is 40, so I get 36 minus 40 inside. 2 times 1 is 2. And here is where I would definitely tell that this is not factorable because my discriminant being underneath the radical, this thing right here, well, what's going to happen when I do 36 minus 40? Well, that's going to give me the square root of negative 4, which means this solution has to be imaginary. As we talked about earlier, the square root of negative 4 can be broken down as square root of 4 times the square root of negative 1. So that's going to give me negative 6 plus and minus. Well, the square root of 4 is 2, and the square root of negative 1 is I all over 2. And as we just talked about 2 slides ago, if I can divide all these 3 things in this triangle, I can do that. I can divide them all by 2. So we would get negative 3 plus and minus I. Now, if I were to do the exact same thing with completing the square, I should get the same answer. Recall that in order to complete the square, you do your b term, you divide it by 2, and you square it. I often move my constant term over. So I'm going to do x squared plus 6x, leave a little space, and I'm actually going to subtract the 10 from both sides. So I get negative 10 over here. And now I look, what is my b term? My b term is still 6. So I'm going to get 6 divided by 2 and square it. 6 divided by 2 would be 3. 3 squared is 9. So I'm going to add 9 to the left-hand side. Well, anytime you add something to one side, you have to add it to the other to remain equal. So I'm going to add 9 over here as well. What's the point of doing all this? Well, this is now factorable. In fact, it's going to be factorable for completing square always. You end up with x plus b over 2. Quantity squared, because conceptually what multiplies to 9 adds to 6. That of course be 3 and 3. So we would get x plus 3, or x plus 3 quantity squared because you've completed the square. And again, where did that 3 come from? It's this 6 divided by 2 step right there. On the right hand side, we get negative 10 plus 9, which would be negative 1. And then from here, we can just solve. I would square root both sides. So I would get x plus 3 equals. We square rooted, so we get plus and minus. Square root of negative 1, as we talked about earlier, was just I. And then we can minus 3. We get x equals. These two cannot be combined, so I'll just leave them as separate. 3 plus and minus I. It's also important to note that these are two different solutions. These are negative 3 plus I and negative 3 minus I. Imaginary solutions always show up in pairs because in order to generate them, we had to square root a negative at some point, which means we get a plus and minus value. By definition of polynomials, the degree, so for example, x to the fourth plus blah, 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 your degree is the highest number of potential solutions. So what interestingly happens is, for example, this has four solutions. It could have four real solutions. It could have two real solutions and two imaginary solutions. It could have zero real solutions and four imaginary solutions. It could never have three imaginary solutions or one imaginary solution. Those are impossible because they always show up in pairs. Interestingly enough, it could only have one real. It could have one real or three real because reals can be repeated. Thank you for listening, and I hope you have a wonderful day.